Quantum mechanics is the branch of physics that describes the behavior of particles on a microscopic scale. Unlike classical physics, which deals with predictable outcomes based on cause and effect, quantum mechanics introduces probabilities and uncertainties. A key concept here is superposition, where particles can exist in multiple states simultaneously until measured. For example, an electron in an atom can be in two places at once. Another critical principle is entanglement, where the state of one particle instantly correlates with another, no matter how far apart they are. These principles form the backbone of quantum computing, enabling it to perform complex calculations much faster than traditional computers. In fact, a quantum computer with just 50 qubits could theoretically outperform today's most powerful supercomputers on specific tasks. As we dive deeper into this fascinating world, let's explore how these concepts translate into practical applications and the future of computing. Quantum computing is all about qubits, which are the building blocks of quantum information. Unlike classical bits that can be either a 0 or a 1, qubits can exist in multiple states simultaneously thanks to superposition. This means a single qubit can represent both 0 and 1 at the same time, effectively doubling the computing power with each additional qubit. For example, while two classical bits can only represent 4 possible combinations, 0, 1, 10, or 11, at any one moment, 2 qubits can represent all these states simultaneously. This ability to process vast amounts of information in parallel is what makes quantum computers so powerful and different from traditional machines. IBM's quantum computer, for instance, has already demonstrated the potential with its 65-qubit processor. As we delve deeper into this technology, the unique properties of qubits will continue to revolutionize how we solve complex problems. Next up, let's explore another fascinating aspect of quantum computing: entanglement. The heart of quantum computing lies two fundamental concepts: superposition and entanglement. Superposition allows particles like electrons to exist in multiple states simultaneously until they are observed. For example, an electron can spin both clockwise and counterclockwise at the same time. This is unlike classical bits that can only be 0 or 1, but quantum bits or qubits can be both 0 and 1 simultaneously thanks to superposition. Entanglement takes this a step further by linking particles in such a way that the state of one particle instantly affects the other, no matter how far apart they are. Albert Einstein famously called it spooky action at a distance. For instance, if two entangled photons are separated and you measure one as spinning clockwise, the other will instantaneously spin counterclockwise. These principles not only make quantum computing theoretically much faster than classical computing, but also pave the way for secure communication through quantum cryptography. As we delve deeper into these phenomena, the potential applications become even more exciting. Quantum computing is exciting, but it's not without its challenges. One major hurdle is quantum decoherence, where qubits lose their quantum properties due to environmental interference. For instance, Google's Sycamore processor has only 53 qubits, and maintaining coherence for more complex systems becomes exponentially difficult. Another challenge lies in error correction. Unlike classical bits, qubits can't just be copied or compared directly because of the no-cloning theorem. This means that quantum computers need sophisticated algorithms to detect and correct errors without disturbing the delicate state of qubits. IBM has been working on this by developing advanced error correction codes, but it's still a work in progress. Despite these challenges, researchers are making strides every day, pushing the boundaries of what we thought possible. As we overcome these obstacles, quantum computing could revolutionize fields like cryptography and drug discovery. Quantum cryptography is one of the most promising applications of quantum computing, offering unprecedented security in communication. At its core, it uses principles like quantum key distribution, QKD, to ensure that any attempt at eavesdropping can be detected immediately. For example, China has already demonstrated this technology on a large scale with their MISHA satellite, which successfully transmitted QKD signals over long distances, ensuring secure communications between Beijing and Vienna. This is crucial because traditional encryption methods are becoming increasingly vulnerable to quantum attacks. In fact, it's estimated that within the next decade, current cryptographic systems could be cracked by advanced quantum computers. As we delve deeper into this topic, let's explore how these quantum technologies will shape our future communication networks. Quantum computing holds incredible potential for solving some of the most complex optimization problems we face today. For instance, in logistics and transportation, optimizing delivery routes can significantly reduce costs and emissions. A classical computer might take years to find the best route among millions of possibilities, but a quantum computer could do it in minutes. Take D-Wave Systems, which has already demonstrated solving certain types of optimization problems faster than traditional computers. In finance, quantum computing can revolutionize portfolio optimization by quickly analyzing vast datasets to find the most profitable and least risky investments. This technology is not just theoretical. Companies like Volkswagen have used quantum algorithms to optimize traffic flow in Beijing, reducing congestion and improving air quality. As we move forward, these advancements will play a crucial role in shaping how businesses operate more efficiently. Next, let's dive into another exciting application: cryptography. Quantum computing and artificial intelligence are two cutting-edge technologies that are increasingly intersecting. Quantum computers can process vast amounts of data much faster than classical systems, which is crucial for AI algorithms that require massive computational power. For instance, Google's quantum computer Sycamore completed a task in 200 seconds that would take the world's most powerful supercomputer 10,000 years to finish. This kind of speed-up can revolutionize machine learning by enabling more complex and accurate models. Companies like IBM are already developing hybrid systems where classical computers work alongside quantum processors to enhance AI capabilities. As we move forward, this synergy could lead to breakthroughs in fields ranging from drug discovery to climate modeling. The potential is immense, but the challenges are significant too. Next, let's explore some of these hurdles and what it takes to overcome them. Quantum computing has the potential to revolutionize many fields. In healthcare, quantum computers could help us model complex biological systems and accelerate drug discovery processes. For instance, researchers at IBM are already using quantum algorithms to simulate molecular structures that could lead to new treatments for diseases like cancer. In finance, quantum computing can optimize portfolios and predict market trends with unprecedented accuracy, according to a report by McKinsey & Company. Quantum computing could unlock up to $2 trillion in value across industries over the next decade. Another exciting area is cryptography, where quantum computers might break current encryption methods, but also enable new forms of secure communication. As we explore these possibilities, it's clear that quantum computing will play a pivotal role in shaping our future technologies and solutions. Quantum computing research is bustling with activity around the world. Companies like IBM and Google are leading the charge, with IBM recently unveiling their Quantum System 2, capable of handling up to 433 qubits. That's a significant leap from just a few years ago when they were working with systems in the single digits. Google has also made waves with Sycamore, which achieved quantum supremacy by completing a task in minutes that would take traditional supercomputers thousands of years. Universities and startups are not far behind, pushing boundaries on everything from error correction to new materials for qubits. For instance, researchers at MIT have developed topological qubits that could drastically reduce the need for complex cooling systems. This rapid progress means we're likely just a few breakthroughs away from quantum computing becoming a game changer in various industries. Next up, let's dive into how these advancements will impact sectors like finance and healthcare. As we delve into the future of quantum computing, it's crucial to consider the ethical implications. One significant concern is privacy. Quantum computers could potentially break current cryptographic systems, putting sensitive data at risk. For example, RSA encryption, widely used for secure transactions, might become vulnerable with a large-scale quantum computer. This raises serious questions about how we can protect personal and financial information in a post-quantum world. Additionally, the environmental impact of quantum computing is another ethical issue. Quantum computers require extremely low temperatures to operate, often achieved using liquid helium, which has its own set of sustainability challenges. As we move forward, it's essential to balance technological advancement with responsible stewardship. Understanding these ethical dimensions will be key as we continue exploring how quantum computing can shape our future. Quantum computing is poised to revolutionize our society in ways we are only beginning to understand. Imagine a world where complex problems that take today's computers years to solve can be cracked in seconds. For example, quantum computers could vastly improve drug discovery processes, potentially cutting down the time it takes to develop new medicines from 10 years to just months. This means faster access to life-saving treatments for millions of people worldwide. In another realm, climate modeling could see a massive leap forward. Quantum computing can process vast amounts of environmental data much more efficiently than classical computers, leading to better predictions and solutions for climate change. As these advancements unfold, they will not only transform industries, but also our daily lives, making everything from healthcare to energy consumption smarter and more efficient. So as we delve deeper into this quantum revolution, let's explore the next big question: how do we prepare ourselves and society for such an impactful shift? As quantum computing continues to evolve, it's opening up a wealth of exciting career opportunities. According to a report by IBM, over the next 5 years, the demand for skilled quantum professionals could grow tenfold. You can find roles in hardware engineering, where you'll work on building and maintaining quantum computers. For instance, companies like Google and Intel are constantly seeking experts who can design new qubit architectures. On the software side, there's a growing need for quantum algorithm developers, people who write code that runs specifically on quantum systems. IBM alone has over 200,000 users on its Quantum Experience platform, indicating the vast interest in this field. Whether you're into research and development or want to apply quantum computing to solve real-world problems, there's a place for you here. As we dive deeper into these opportunities, let's explore some of the leading companies at the forefront of quantum technology. Quantum computing holds immense potential, but also poses significant risks. One major concern is quantum hacking, where powerful quantum computers could break current cryptographic systems. For instance, RSA encryption, widely used for secure data transmission, might become vulnerable. According to a report by the National Institute of Standards and Technology, NIST, a large-scale quantum computer could crack an RSA 2048 encryption in just 8 hours. This threat is so serious that governments and tech companies are already developing post-quantum cryptography methods. Another challenge is the technical complexity of building stable, error-free quantum computers. Quantum bits, or qubits, need to maintain coherence for computations to be accurate, which is incredibly difficult given environmental disturbances. As we navigate these risks, it's clear that careful planning and robust security measures are essential. Next, let's explore how businesses and governments are preparing for this quantum leap. Quantum computing is poised to revolutionize technology in ways we can barely imagine today. For instance, Google's Sycamore processor achieved quantum supremacy by performing a computation in 200 seconds that would take the world's fastest supercomputer 10,000 years to complete. This kind of processing power could transform industries from pharmaceuticals to financial services. In drug discovery alone, quantum computing could drastically reduce development times and costs by simulating molecular interactions far more efficiently than classical computers can manage. Looking ahead, quantum networks will enable ultra-secure communications, potentially making data breaches a thing of the past. As we move forward into this new era, it's clear that quantum computing will not just enhance existing technologies, but also create entirely new possibilities. Next up, let's explore some of these emerging applications in more detail.